Between the orbits of Mars and Jupiter lies a thin ring of stone and metal, the asteroid belt, a quiet collection of leftovers from the solar system's birth. It sits about 300 million kilometers from the Sun, a narrow band that stretches roughly 300 million kilometers across. In that space, the Sun's gravity holds a swarm of fragments that never gathered into a planet. The total mass of the belt is tiny, about 4% of the Moon's mass, or roughly 1/10,000th of Earth's. That number feels almost absurd when you picture the countless rocks that fill the region. I find it hard to picture a mass that's small spread over such a vast volume. Most of the objects are irregular, ranging from dust-sized grains to the dwarf planet Ceres, which alone accounts for about a third of the belt's mass. The rest are a jumble of boulders and metallic chunks, each a relic of the early protoplanetary disk. Their surfaces are scarred by countless collisions, a record of a chaotic past. Composition varies. Some bodies are rich in silicate rock, the same material that makes up much of Earth's crust. Others are heavy with iron and nickel, hinting at the cores of differentiated planetesimals that were shattered long ago. The mix tells a story of a region where temperature and pressure never allowed a single, uniform planet to form. Why didn't a planet emerge here? The dominant answer points to Jupiter's gravity. As the gas giant grew, its massive pull stirred the belt, increasing relative speeds among the fragments. Those speeds stayed high enough that collisions were more likely to break apart than to stick together. In a laboratory, you would see the same effect, a shaking table that keeps grains from settling into a solid mass. The belt's location also matters. It lies just beyond the snow line, where volatile ices could survive in the early disk. Yet the material here is largely dry, suggesting that any ice that was present was either vaporized or never abundant enough to aid accretion. That subtle temperature gradient, combined with Jupiter's perturbations, left the belt as a graveyard of unfinished building blocks. Even with its modest mass, the belt exerts a measurable influence on its neighbors. Mars, the planet closest to the inner edge, experiences occasional impacts from belt fragments that stray inward. Those impacts have helped shape its thin atmosphere and cratered surface. Jupiter, on the outer side, feels a faint tug that contributes to the overall stability of its own orbit. The gravitational dance is delicate. A shift in the belt's mass distribution could ripple outward. Astronomers have measured the belt's total mass through spacecraft flybys and telescopic observations. The numbers converge on that 4% of the Moon figure, but uncertainties remain. We don't really know the exact distribution of mass among the countless small bodies, because most are too dim to detect individually. The bulk of the belt's weight hides in the invisible dust that glows faintly in infrared light. The belt also serves as a time capsule. Its rocks preserve the chemical fingerprint of the solar nebula, the cloud of gas and dust that birthed the Sun and planets. Samples returned by missions such as Hayabusa 2 and OSIRIS-REx show isotopic ratios that match primitive meteorites found on Earth. Those isotopes are a reminder that the belt is not just debris. It is a snapshot of the system's earliest chemistry. Dynamic processes continue to stir the belt today. Resonances with Jupiter create gaps, known as Kirkwood gaps, where the gravitational pull clears out orbits. Objects that wander into these resonances can be nudged onto trajectories that cross Earth's path, becoming near-Earth asteroids. In that sense, the belt is a source of both hazard and opportunity for our planet. The belt's thickness is modest compared to its width, only about 1/10 of an astronomical unit thick. Yet within that slab, the density of objects is low enough that a spacecraft can traverse it with minimal risk, as demonstrated by the Dawn mission's orbit around Vesta and Ceres. The feeling of moving through a region where you might see a speck of rock a few kilometers away, then nothing for hours is oddly unsettling. From a planetary formation perspective, the belt illustrates a boundary case. It shows that not every region of a protoplanetary disk ends in a full-size world. The combination of location, mass, and external gravity can freeze the accretion process halfway. That outcome is a reminder that the architecture of a solar system is not predetermined. It is the product of many competing forces. When we look at other star systems, we sometimes detect debris disks that resemble our belt, rings of dust and rock left over after planet formation. Those observations suggest that our belt is not unique, but a common byproduct of planetary birth. Still, each disk has its own quirks, shaped by the particular giants and the timing of their growth. In the lab, we might try to recreate a belt by stirring a mixture of sand and metal fragments in a rotating drum, watching how they clump, or fail too. The result would be a messy, ever-changing heap, never quite settling into a solid sphere. That analogy captures the essence of the asteroid belt, a persistent, restless collection that resists the final step toward planetary status. Even as we catalog its members and map its orbits, the belt retains an element of mystery. The exact number of objects larger than a kilometer remains an estimate, and the total mass could shift if a hidden population of dark, carbon-rich bodies lurks unseen. The fact that we can only approximate these values reminds us of the limits of our measurements. One detail that often goes unnoticed is the faint glow of zodiacal light, a diffuse band visible just after sunset or before sunrise. That glow is sunlight scattered by the tiny dust particles that drift outward from the asteroid belt, a subtle reminder that even the smallest fragments contribute to the system's overall appearance. The belt's quiet presence, sandwiched between two planets, offers a steady backdrop to the more dramatic motions of the inner and outer solar system. Its mass is small, its influence modest, yet its role as a reservoir of primordial material makes it a key piece in the puzzle of how our planetary neighborhood came to be. A single grain of dust, caught in the sun's weak pull, drifts slowly through this region, reflecting a faint glint that would be invisible without a telescope. That glint, fleeting and tiny, is the only hint we have of the countless particles that fill the space between Mars and Jupiter. The nebular hypothesis tells us that the Sun and the planets began as a rotating cloud of gas and dust. That cloud collapsed under its own gravity, flattening into a thin, spinning disk. In that disk, tiny solid grains collided gently, sticking together like wet sand on a beach. Those grains grew into millimeter-sized pebbles, then into centimeter clumps, and the process repeated. At first, the collisions were slow, the particles moving at only a few meters per second. I find it hard to picture how such a sluggish dance could build something as massive as a planet. When enough pebbles gathered, their mutual gravity became noticeable. A handful of meters-wide bodies began to pull in surrounding material, entering the planetesimal stage. Planetesimals are kilometer-scale rocks that dominate the local mass budget. Their gravity accelerates nearby dust, making collisions faster and sticking more likely. The next step is called runaway growth. A slightly larger planetesimal sweeps up material faster than its smaller neighbors, pulling ahead like a snowball rolling downhill. Runaway growth requires a threshold, roughly a few hundred kilometers across, where gravity overpowers random motions. Below that size, collisions tend to fragment rather than accrete. If a body reaches the critical mass for hydrostatic equilibrium, its self-gravity can compress the interior enough to become round. That marks the birth of a protoplanet. Protoplanets continue to collide, sometimes merging, sometimes shattering each other. The timescale for these events stretches over millions of years, not weeks. During this epoch, the giant planets already loom large. Jupiter, sitting beyond the snow line, exerts a powerful gravitational pull on everything inside its orbit. Jupiter's stirring effect raises the relative speeds of planetesimals in the inner disk. Higher speeds mean more energetic impacts, which often break bodies apart. Because of Jupiter's influence, the region between Mars and Jupiter never settles into a calm accretion environment. It remains a chaotic sea of fragments. The asteroid belt sits precisely in that disturbed zone. Its material never reached the runaway growth threshold before Jupiter kept shaking it up. If the belt had been farther from Jupiter, the same amount of mass might have formed a planet. Distance matters as much as raw material. Even with the same mass, the belt's composition matters. It is rich in volatile poor rock, lacking the icy ices that helped outer planets grow quickly. The lack of ices reduces the surface density of solid material, slowing the accretion rate. Slower growth makes it harder to outrun disruptive collisions. Models suggest that, without Jupiter's perturbations, the belt could have produced a body a few hundred kilometers across in a few million years. That is still far from planetary size. In reality, Jupiter's gravity kept the relative velocities above the fragmentation barrier. Bodies kept breaking apart faster than they could combine. The result is a belt of millions of objects ranging from dust grains to dwarf planet Ceres. It is a snapshot of a failed planetary nursery. We don't really know how close the belt came to the runaway threshold. Observations only give us present-day sizes, not the ancient collision history. Some simulations show brief periods where a handful of planetesimals grew larger, only to be shattered later by a Jupiter-induced impact. Those brief flashes of growth left no lasting trace. The timescale for runaway growth is also sensitive to the overall mass of the disk. If the early solar nebula had been denser, the belt might have crossed the threshold before Jupiter formed. But the Sun's birth environment likely limited the total mass available. The protoplanetary disk dispersed after a few million years, cutting off the supply of fresh material. When the gas vanished, aerodynamic drag weakened, and the remaining solids lost the damping that helped them settle into a thin layer. The belt stayed puffed up, making collisions more violent. Thus, the combination of Jupiter's stirring, low ice content, and limited time prevented the belt from becoming a planet. Each factor nudged the system away from the runaway path. If we compare the belt to the terrestrial planets, the difference is stark. Earth and Venus amassed enough mass quickly enough to enter hydrostatic equilibrium and retain an atmosphere. Mars, smaller and farther out, barely reached that point, and its thin atmosphere hints at a marginal growth history. The belt never passed that marginal line. The notion of a planet forming there is tempting, but the physics of accretion set clear limits. Gravity, speed, composition, and time all conspire to shape the outcome. Even a modest increase in Jupiter's orbital eccentricity would have amplified its perturbations. The belt would have been even more hostile to growth. Conversely, a less massive Jupiter might have allowed a few larger bodies to survive, perhaps leading to a small planet. The present configuration is a delicate balance. In modern observations of exoplanetary systems, we see gaps in disks that hint at unseen giants sculpting the material. Those gaps often correspond to regions where planet formation stalled. Our own belt is a local example of that phenomenon, a fossil record of where a giant planet's influence halted growth. It is a reminder that not every ring of material becomes a world. The story of the belt's failure is not a failure at all. It is a natural outcome of the same processes that built the other planets. The same physics that made Earth possible also kept the belt as dust. When we look at the belt today, we see a mixture of metallic iron, silicate rock, and a sprinkling of carbon-rich material. Those ingredients tell us about the temperature gradient of the early disk. The temperature at the belt's distance was high enough to vaporize most volatiles, leaving behind dry, dense particles. Those particles are less sticky than icy grains, slowing growth. We can measure the size distribution of belt objects with telescopes, and the distribution follows a power law that matches a collisional cascade. That pattern supports a long history of grinding. The cascade continues today as meteoroids strike each other and produce finer dust that spirals into the sun under radiation pressure. The belt is still being ground down. Even though the belt never became a planet, it still plays a role in delivering material to the inner solar system. Some meteorites that fall on Earth originated in the belt. Those meteorites carry clues about the early solar system's chemistry, preserving isotopic signatures that we cannot find elsewhere. They are tiny messengers from a time we cannot observe directly. In the end, the belt's existence hinges on a narrow set of conditions that prevented runaway growth. It is a quiet counterexample to the more dramatic planetary births we often imagine. If you stare at the night sky and notice the faint glow of zodiacal light, you are seeing sunlight scattered by dust from that very belt. The dust is a lingering reminder of the unfinished story. The asteroid belt today is a thin band of gravel, each piece feeling the tug of the sun and the restless pull of Jupiter. To turn that spread of rock into a single world, the first hurdle is mass. Current estimates place the belt's total weight at about 4/100ths of Earth's, far below the threshold where gravity can overcome the random motions of the fragments. I find it hard to picture a sudden jump from a handful of moons to a planet-sized core without an external shove. One way to increase the mass is to add material from elsewhere. A passing comet swarm, a disrupted dwarf planet, or the remnants of a lost moon could dump enough rock to tip the scales. Even then, the added weight would need to be concentrated, not just scattered. Gravity only starts to dominate when the combined mass reaches roughly 1/10 of Earth's, a figure that sits well beyond the belt's natural inventory. Jupiter's presence complicates the picture. Its gravity stirs the belt, injecting orbital eccentricities that keep the rocks from settling. To suppress those perturbations, Jupiter would have to move outward, lose some of its mass, or be temporarily silenced by another massive body. The idea of a sudden loss of a gas giant feels like a laboratory accident, an improbable but not strictly forbidden shift in the system's architecture. A massive impact could provide the necessary disturbance. Imagine a rogue protoplanet several hundred kilometers across, slamming into the belt at several kilometers per second. The collision would vaporize a portion of the material, creating a dense cloud of dust and molten fragments. In that cloud, collisions become sticky. Surface tension and cooling allow particles to clump more readily than in the cold vacuum of space. The aftermath of such an impact would be a temporary reduction in Jupiter's influence, simply because the debris cloud would absorb some of the planet's resonant energy. During this lull, the dense swarm could begin to accrete. Accretion under these altered dynamics is not instantaneous. Models suggest a timescale of a few million years, far slower than the rapid collapse one might expect in a quiet nebula. Stability of a growing core is another concern. As clumps merge, their gravity deepens the local well, pulling in more material. Yet each addition also stirs the surrounding particles, injecting kinetic energy that can fling fragments outward. The balance between gathering mass and shedding it is delicate. In the lab, we see similar behavior when fine powders are shaken. They form temporary arches that collapse under their own weight. If the core reaches a size comparable to Mars, its own gravity begins to dominate the local environment. At that point, the surrounding belt would start to thin, feeding the planet rather than remaining a ring of loose rock. The process would be self-reinforcing. A larger planet clears its orbit, leaving a gap that widens over time. This clearing is what we observe in the gaps of protoplanetary disks around young stars. Feasibility within known physics remains shaky. The required mass increase is an order of magnitude larger than the belt's current inventory, and the suppression of Jupiter's perturbations demands a scenario we have not observed elsewhere. We do not really know whether a gas giant can lose enough of its influence without destabilizing the whole inner system. The mathematics allow a narrow window, but the natural probability looks slim. Even if the mass hurdle were cleared, the temperature of the belt matters. At roughly 2 astronomical units from the Sun, the ambient heat is low enough that most rock stays solid, but not so low that volatile ices are completely frozen out. A sudden influx of heat, perhaps from the impact itself, could melt portions of the material, creating a transient magma ocean. That liquid layer would flow, smoothing irregularities, and could accelerate the coalescence process. Radiation pressure from the Sun also plays a subtle role. Small grains feel a push that can loft them out of the belt, while larger boulders remain anchored by gravity. In a dense cloud, the collective surface area grows, increasing the net effect of radiation pressure. This could act as a brake on accretion, bleeding off the finest dust and leaving behind a more coarse assemblage. The orbital dynamics of the growing planet would shift as its mass climbs. Its semi-major axis would drift slightly under the combined pull of the Sun and the remaining belt material. This drift could move the planet into a region where Jupiter's resonances are weaker, further protecting the nascent world from disruptive kicks. The shift would be on the order of a few hundredths of an astronomical unit, small enough to escape casual detection, but enough to matter for long-term stability. A potential trigger that does not involve an impact is the loss of one of the outer gas giants. If Saturn were ejected from the solar system by a passing star, the overall gravitational balance would change. Jupiter's resonances would weaken, and the belt could experience a period of relative calm. During that calm, the existing mass could slowly knit together, though the timescale would stretch to tens of millions of years. In all of these scenarios, the key variable is the rate at which kinetic energy can be dissipated. Collisions at high speed tend to bounce, preserving energy and preventing sticking. To convert kinetic energy into heat, the fragments must be small enough for surface forces to dominate, or the collisions must happen at low relative velocities. The impact-generated cloud offers both conditions: fine particles and reduced speeds. Observationally, we have never seen a full-scale belt collapse in our own system, but exoplanet surveys reveal systems where a dense ring of debris sits just inside a massive planet. Those configurations hint that nature can, under the right circumstances, push material inward. Whether the process ever completes to the point of a solid world is still an open question. If such a planet formed, its composition would mirror the belt's mixed inventory: metallic iron, silicate rock, and a sprinkling of carbon-rich material. Its density would be lower than Earth's, more like that of Mars, reflecting the high proportion of lighter silicates. Surface gravity would sit at roughly half Earth's, enough to retain a thin atmosphere if volatile gases survive the formation burst. The final picture is a world that never quite fits the classic definition of a planet, perched where a ring once was, its existence a quiet testament to a rare set of conditions. One can imagine standing on its dusty plain, feeling the faint pull of the Sun, looking outward to the faint outline of Jupiter's cloud bands on the horizon. The faint, steady hiss of micrometeorites still striking the surface would be the only reminder that the belt once stretched far beyond the horizon. The numbers that pop up in the simulations are stubbornly small, a radius somewhere between 600 and 900 kilometers. That puts the object in the dwarf planet regime, not a full-blown terrestrial world. Its silhouette would barely fill a telescope's field of view, a faint disk against the sun's glare. It is easy to imagine a sphere that size, but I find it hard to picture the mass that would hold it together. If the belt's fragments managed to stick, the bulk would be a mixture of iron, nickel metal, and silicate rock, the same ingredients that make up the larger planets. The metal would be scattered in pockets, the silicates forming the majority of the crust. The ratio would be far from the Earth's, leaning toward the lighter side because the belt never gathered enough mass to compress the metal into a dense core. In a lab note, I would mark the composition as mixed metallic silicate, low metal fraction. That mixture translates directly into a low bulk density. Earth's average is about 5.5 gcm3. Our hypothetical planet would sit closer to 3 grams per cubic centimeter, maybe a touch less. The numbers come from adding up the known densities of C-type asteroids and the few metallic M-type bodies that drift through the belt. The result feels almost counterintuitive, a body the size of a small moon that is more like a loose pile than a solid rock. We don't really know how that would affect internal pressure, but the calculations suggest a gentle squeeze, nowhere near the crushing forces at the center of Earth. Because the mass is modest, the gravitational pull at the surface would be weak. Surface gravity would hover between 5 and 10% of Earth's. A person would weigh about 5 kilograms on a 10-kilogram mass. The feeling would be odd. You could lift a rock the size of a small car with one hand, yet you would still feel a faint tug pulling you down. The low gravity also means that any gases trying to cling would escape quickly. That brings us to the atmosphere, or rather its absence. With such a feeble pull, volatile molecules would reach escape velocity after only a few collisions. Even if the belt's material contained water, ice, or frozen carbon compounds, the heat from solar radiation would vaporize them, and the particles would drift away into space. The result is a near-vacuum envelope, perhaps a tenuous exosphere composed of stray sodium atoms, the sort that cling to Mercury for a few minutes before disappearing. No weather, no clouds, just the thin whisper of solar wind brushing past. The surface itself would be a blanket of regolith, the fine dust that coats most asteroids. Impacts over billions of years would have shattered larger rocks, grinding them into a powdery layer a few meters thick at most. The grains would be jagged, metallic specks mixed with silicate shards, each one remembering a collision that happened eons ago. In low gravity, the regolith would not settle into dunes. Instead, it would cling loosely, shifting when a foot or a rover presses down. The sound of a footfall would be a muted thud, the dust puffing outward like a brief cloud of ash. Beneath that dust, the interior would lack the sharp differentiation we see on Earth. Without enough pressure to melt the metal into a central core, the planet would remain a loosely bound aggregate. There might be a modest concentration of metal toward the center, but it would not form a solid sphere. Instead, the interior could be a porous matrix, pockets of voids interspersed with rock and metal. The overall rigidity would be low. A strong impact could send shockwaves that reverberate through the body, shaking it like a bell rather than cracking it. Temperature on the surface would be dictated primarily by distance from the sun, roughly the same as the asteroid belt's average, about 170 Kelvin at perihelion, rising to near 200 Kelvin at aphelion. The thin regolith would have little insulating power, so the surface would cool quickly after sunset, the night side plunging into a deep cold. Daylight would warm the top millimeter of dust, but the subsurface would stay close to the mean temperature. No greenhouse effect to speak of, just the raw balance of solar input and radiative loss. Because the gravity is weak, the escape velocity would be on the order of a few hundred meters per second. A modest launch from the surface could fling material into orbit, perhaps forming a thin ring of debris that slowly drifts away. Any natural satellite would have to be captured, not formed in situ. The planet's pull is simply not strong enough to hold a large moon in a stable orbit for long. If a spacecraft managed to land, the touchdown would feel like stepping onto a very soft mattress. The legs would sink a few centimeters into the powder, then settle. The instrument readings would show a pressure of only a few pascals, barely enough to register on a sensitive barometer. The visual field would be dominated by a horizon that rolls away gently, the curvature barely perceptible over several kilometers. Light from the sun would scatter off the fine dust, giving the sky a faint, hazy glow not unlike the twilight on a desert planet. One small detail that sticks in my mind is the way a single pebble rests in a shallow depression, its shadow half a millimeter long, trembling as a micrometeor passes overhead. The asteroid belt, now a solid world, would sit between Mars and Jupiter. Its mass might be a few percent of Earth's, enough to be felt. I find it hard to picture a rock-filled sphere where dust once drifted, but the numbers are stubborn. First, Mars would feel the pull. Its semi-major axis, currently 1.52 AU, would shift outward or inward depending on the new planet's exact position. A modest increase of a few hundredths of an AU would change the length of a Martian year by weeks. That change sounds small, yet the orbital energy budget is delicate. A slight alteration can move Mars closer to a mean motion resonance with the new planet. Mean motion resonances are like ticking clocks. When two bodies complete orbits in a simple integer ratio, their gravitational nudges line up. If the new planet sits near 2, one with Mars, every second Martian lap would meet the same side of the planet. Over millions of years, that repeated tug could pump Mars's eccentricity, making its path more elongated. I don't have a clear picture of how quickly that would happen. The math grows messy beyond simple two-body approximations. Jupiter, the heavyweight of the system, would not stay still either. Its orbit at 5.20 AU is held by a balance of solar gravity and its own inertia. Adding a few Earth masses between it and the Sun adds a new term to the balance sheet. The giant could be nudged inward by a few thousandths of an AU, or it might migrate outward if angular momentum is transferred the other way. The direction depends on how the new planet's orbital speed compares to Jupiter's. We don't really know which scenario dominates without a full N-body simulation. If Jupiter drifts even slightly, the whole set of resonances that sculpt the asteroid belt would shift. The Kirkwood gaps, regions cleared by resonances, would move, leaving some fragments in new stable zones and exposing others to chaotic wandering. The remaining debris, those tiny rocks that never coalesced, would feel a reshaped gravitational landscape. Some would settle into new, long-lived orbits, while others would be tossed toward the inner planets. Earth's orbit is the most sensitive to changes in the outer system. Its eccentricity today oscillates between about 0.005 and 0.06 over 100 Kerr cycles, driven partly by Jupiter's pull. If Jupiter's semi-major axis shifts, those cycles would be altered. A small increase in Jupiter's distance could lower the forced eccentricity on Earth, making the climate's long-term rhythm a bit smoother. Conversely, an inward drift could raise Earth's eccentricity, stretching the seasonal contrast over tens of thousands of years. The effect would be subtle, perhaps a few hundredths of a degree in orbital shape, but enough to be recorded in ice cores if the planet survived long enough. The combined influence of Mars and Jupiter moving creates a web of secular resonances. These are slower, long-term exchanges of angular momentum that can tilt orbital planes or stretch ellipses. In a system where the new planet sits at 2.7 AU, its own precession rate could match that of Mars, leading to a secular resonance that pumps Mars's inclination. That would tilt Mars's orbital plane by a degree or two, changing the angle at which it meets the Sun. Such a tilt is tiny compared to the 1.85 degrees inclination we measure now, but over hundreds of millions of years it could accumulate. Stability of the inner planets, Mercury, Venus, Earth, and Mars, depends on the absence of strong resonant forcing. Introducing another body of appreciable mass adds a new frequency to the system. If that frequency coincides with the natural precession of Mercury's perihelion, Mercury could experience a chaotic cascade. The planet's orbit might become unpredictable on a timescale of tens of millions of years. We have seen similar behavior in computer models where a modest mass is placed near 0.4 AU. The inner system can tip into chaos. I admit it is hard to say whether the new planet would sit at a dangerous harmonic or remain safely out of phase. Long-term evolution could settle into a new equilibrium, or it could descend into chaos. In some simulations, adding a 0.02 Earth mass body between Mars and Jupiter leads to a quasi-stable configuration after a few 100 million years. The planets settle into slightly altered distances, resonances realign, and the system settles into a new rhythm. In other runs, the same mass triggers a chain reaction. Mars's eccentricity climbs, crossing Earth's orbit, and a series of close encounters ejects one of the inner planets. The outcome is highly sensitive to the exact initial conditions, position, velocity, and even the distribution of the leftover asteroid fragments. The leftover fragments themselves act as a dampening medium. Collisions among them convert orbital energy into heat, slowly circularizing their paths. If the new planet's gravity keeps many fragments in crossing orbits, the collision rate rises, producing a faint, persistent dust cloud. That cloud would add a subtle drag on the planet's motion, a non-gravitational effect that could marginally slow its outward migration. The drag is minuscule, perhaps a few millimeters per second per year, but over billions of years it could shift the final orbital radius by a fraction of a percent. One concrete clue we could look for, if such a planet existed, is the precession rate of Mars's perihelion. In our current system, it advances by about 0.53 degrees per century, a value that matches predictions from general relativity and planetary perturbations. A nearby massive body would add a term to that rate, measurable as a deviation of a few hundredths of a degree over a century. Detecting such a drift would require decades of precise tracking, but the signal would be there, a tiny wobble in the data. The final picture remains fuzzy. Gravitational tugs, resonant locks, and slow drifts intertwine in a dance that is easy to sketch but hard to resolve. What is clear is that a planet born from the asteroid belt would not sit quietly. It would reshape the orbital architecture, nudging Mars, tugging at Jupiter, and whispering through Earth's eccentricity. The solar system would find a new balance, or perhaps fail to find one at all. The most immediate evidence would be a slight, steady change in the angle at which Mars's orbit crosses the ecliptic, a tilt that grows imperceptibly each millennium. I sit back, notebook open, and try to picture a new planet where the asteroid belt once lay. The material that now swirls between Mars and Jupiter would be squeezed into a body perhaps a few 100 kilometers across, perhaps a little more. My hand pauses on the page because the consequences for Earth feel both obvious and oddly opaque. If the new planet occupies the same average distance as the original belt, its gravity will be modest, perhaps a few percent of Earth's, but enough to perturb nearby small bodies. I write down the first question that comes to mind. Will Earth see more or fewer impacts? The answer depends on how the planet reshapes the local gravitational landscape. On one hand, the planet could act as a scatterer, nudging asteroids into new paths that intersect Earth's orbit. A single close pass of the planet might increase the eccentricity of a neighboring asteroid by a fraction of a degree, enough to turn a harmless passerby into a threat. I calculate a rough scattering cross-section and find it comparable to the combined cross-section of the original swarm. That suggests a modest rise in impact frequency, perhaps a few percent over the long term. On the other hand, the planet could act as a shield. Its presence may capture many potential Earth crossers, either by accretion or by diverting them into stable resonances that keep them away from the inner system. The idea of gravitational shielding feels a little loose, but the physics is clear. A massive body can mop up bodies that would otherwise wander inward. I note that Jupiter already plays a similar role, and adding another body may tip the balance toward fewer cometary intruders. I find it hard to picture the net effect without a full-end body simulation. My pen scratches a line of doubt into the margin. We don't really know how the system will settle. Still, the basic intuition is that the planet will both scatter and capture, and the net change could be small, perhaps within the range of historical variability of impact rates. The second point I consider is the possibility of fresh material being delivered to Earth. The new planet, being a collection of metal-rich and ice-rich bodies, would likely retain pockets of water ice and metallic iron that survived the early solar system. If a collision were to eject a slab of this material toward the inner system, Earth might receive a modest influx of metal and water. I write a note. Potential for a single, relatively large impact delivering a few 100 million tons of iron. That is a drop in the ocean of Earth's total metal inventory, but it could be locally significant for a mining operation or for a narrow band of oceanic life. The timing of such deliveries is uncertain. The planet would be in a relatively stable orbit, but occasional impacts by rogue test bodies could knock off debris. I admit that my mental picture of a fresh delivery feels a bit too cinematic. In reality, the amounts would be incremental, not a sudden flood. Still, a handful of metallic meteorites with a composition distinct from the typical chondrites would be a tangible signature of the new planet's influence. A more subtle effect concerns how Earth's climate might feel the presence of the planet. The new planet will reflect a small fraction of sunlight that the original loose belt reflected. The change in the solar radiation that reaches Earth is tiny, perhaps a few tenths of a percent, but it is not zero. I note a potential shift in the Earth's albedo, a slight brightening of the night sky in the zodiacal band. The change could be enough to nudge the top of the atmosphere's temperature by a fraction of a degree. Over geological timescales, such a shift might influence the delicate balance of ice age cycles, though the effect would be dwarfed by Milankovitch variations. I pause to consider the indirect consequences of an altered Earth-Sun distance that might arise if the planet's gravity pulls the inner planets ever so slightly inward. The effect is likely on the order of a few hundredths of an astronomical unit at most. That would translate into a fractional increase in solar irradiance of perhaps 0.5%, again, a modest nudge. My hand slips over the page, writing possible modest warming, and then pauses. It doesn't quite make sense when you say it aloud. How much of a difference does 0.5% really make? The answer is that it would be comparable to a gentle tilt in the Earth's axial tilt, enough to be noticed in the climate record but not enough to cause a runaway. The fifth angle I explore is how the new planet might affect the stability of Earth's orbit itself. The planet will introduce a new secular term in the system's harmonic series. In the long term, this could lead to a slight shift in the precession of Earth's perihelion. I write a line of caution. Potentially alters the timing of seasons by a few days over million-year periods. Such a shift would be slow, and humanity would likely adapt without noticing. The period of Earth's orbital period would remain essentially unchanged. Finally, I look at the prospect of the planet becoming a resource for humanity. A body that already exists in a relatively nearby orbit could be a prime target for extraction of metals, water, and perhaps even rare Earth elements. The logistics of launching a cargo from Earth to a body at 2.5 AU are not trivial, but they are less demanding than a deep-sea mine or a lunar base. I note that the material would be fresh, in the sense of being less weathered than Earth's surface material, which might be advantageous for certain industrial processes. The potential for a new source of titanium, nickel, and water ice could influence the economics of space industry, perhaps easing the pressure on Earth's own reserves. I also write a side note about the risk of inadvertently releasing debris that could become a new hazard for Earth. Any mining operation will inevitably create dust and fragments that may be scattered by the planet's weak gravity. A few millimeter-scale pieces could find themselves on Earth-crossing trajectories, adding to the background of micrometeorite flux. The net effect is probably negligible, but it is a reminder that benefits come with side effects. In the middle of all these considerations, I find a small detail that seems to anchor the whole picture. The night sky would show a faint, steady band of light where the new planet sits, a narrow band of scattered sunlight that would be brighter than the original zodiacal light but still faint. That band would be a constant, almost unnoticed, reminder of the planet's presence, and it would be the first thing a night watcher might notice if they looked closely enough. The band would be a narrow line of light, barely wider than a hand-held telescope's field of view, drifting across the middle of the zodiac. I start by sketching the new inner edge of the habitable zone, now pushed outward by the added mass between Mars and Jupiter. The extra planet's gravity would tug the sun's warmth a little farther, reshaping where liquid water could linger on a world's surface. In practice, that means the classic Goldilocks band moves a few percent outward. Mars finds itself a shade cooler, while the inner edge of the zone slips past the orbit of the newly formed planet. If Mars receives less solar energy, its thin atmosphere would struggle even more to keep heat near the ground. The planet's already fragile greenhouse effect would be squeezed, perhaps turning the already cold highlands into permanent permafrost. I find it hard to picture how much colder the surface would become, because the exact atmospheric composition is still a matter of speculation. Still, the shift is enough to tilt the balance between occasional melt events and a permanently frozen world. At the same time, the new planet would become a source of impactors, not a sink. Its gravity would scatter leftover debris outward, sending a fresh stream of rocks toward Mars. Those rocks, rich in carbon-bearing compounds, could increase the delivery of organics that have been scarce since the early solar system. The timing matters. A surge of organics a few 100 million years after the planet's birth might give nascent microbes a better chance to arise. Yet we do not really know how efficiently those fragments would survive the journey through the thin Martian atmosphere. The same scattering would affect the moons of the outer planets. Jupiter's Galilean satellites sit in a region now crowded by a massive neighbor, and the altered gravitational landscape would modify the tidal forces they feel. Tidal heating, which already keeps Europa's subsurface ocean from freezing solid, could be nudged either up or down depending on orbital resonances. A modest increase might deepen the ocean, while a decrease could allow ice to thicken. The precise outcome hinges on the new planet's orbital eccentricity, a detail we can only guess at. For Saturn's moons, the story is similar but quieter. Enceladus, with its geysers, relies on a delicate balance of tidal flexing. If the new planet's pull reduces that flexing, the plumes could wane, cutting off a possible source of organic material to the surrounding space. Conversely, an enhanced flex could make the geysers more vigorous, spilling more water vapor into Saturn's rings. I admit I find it hard to picture the exact magnitude of those changes without a full dynamical model. Further out, the outer planets would see a change in the rate of meteoritic rain. The new planet would act like a barrier, intercepting some of the comets that would otherwise head toward Uranus and Neptune. their surfaces would receive fewer fresh impacts, perhaps slowing the delivery of volatile compounds that could seed subsurface oceans. In reverse, bodies that happen to be nudged inward might experience a brief spike in impact frequency, a pattern that would be hard to disentangle from the background flux. These variations feed directly into panspermia ideas. If life ever took root on Mars, the altered impact flux could either fling more material outward toward the inner planets or trap it within the new planet's sphere of influence. The probability that a rock bearing microbes reaches Earth would be reduced if the new planet captures a large share of ejecta. On the other hand, a handful of fragments might be flung past the new planet's orbit, reaching the outer solar system more readily. We don't really know which side would dominate. When we compare this hypothetical system to exoplanet surveys, the lesson is subtle. Many observed planetary systems show a dense belt of material just inside a giant planet, yet they lack a full-size world there. If a belt does collapse into a planet, the resulting shift in habitable zone boundaries and impact regimes could explain why some systems appear barren while others host multiple rocky worlds. The new planet would serve as a test case for how planetary mass distribution reshapes habitability. In practice, the presence of an extraplanet would force us to rethink the criteria we use to flag a system as potentially habitable. The simple distance from star rule would need a correction for the gravitational tug of nearby massive bodies. That correction would be small for most distant planets, but for those hugging the inner edge it could be decisive. It suggests that future catalogs should include a term for neighboring mass when estimating surface temperatures. The altered delivery of organics to Mars also has a knock-on effect for any putative subsurface habitats. If more carbon-rich material arrives, the chance that a pocket of water-rich rock hosts a chemistry capable of supporting life rises. Yet the same impactors could also sterilize surface niches with shock heating, creating a trade-off between supply and destruction. The net balance is something we can only estimate with rough numbers. Tidal heating changes for nearby moons might also influence their magnetic environments. A slightly hotter interior could drive a stronger dynamo, generating a protective magnetic bubble that shields a moon's surface from solar wind. That shield could preserve delicate organic molecules for longer periods. Conversely, a cooler interior could weaken the field, exposing the surface to harsher radiation. The direction of the shift depends on the exact resonance pattern set up by the new planet's orbit. Meteoritic influx to the outer planets could also affect the chemistry of their upper atmospheres. Fewer incoming bodies mean a slower replenishment of certain gases that are otherwise lost to space. Over billions of years, that could change the observed spectra of those planets, a detail that might be misread as a sign of different formation histories. In that sense, a single extraplanet can masquerade as a whole different evolutionary path. The panspermia scenario also touches on the timing of life's appearance elsewhere. If the new planet's formation coincides with a lull in impact activity, it could create a quiet window during which life on Mars, if present, might spread outward without being constantly bombarded. If, however, the planet's formation triggers a cascade of collisions, any nascent biosignatures could be erased before they travel far. The timing is a variable that we cannot pin down without a full chronology. From an observational standpoint, the presence of a massive belt-derived planet would be evident in the orbital precession of nearby bodies. Small changes in the longitude of perihelion for Mars, for instance, would betray the extra gravitational pull. Those changes would be measurable with precise tracking, offering a way to test the hypothetical scenario. It would also give us a concrete number to plug into habitability models. Finally, I note a small detail that often goes unnoticed. The new planet's surface would likely be a patchwork of metallic cores and rocky crusts, a relic of the belt's original composition. That heterogeneity could produce localized magnetic anomalies, detectable as faint variations in the solar wind's interaction with the planet. Those anomalies would be a quiet reminder that the planet is, at its heart, a collection of many smaller pieces welded together. The newly formed body, let's call it a planet for the sake of reference, sits where the asteroid belt once lay, sandwiched between Mars and Jupiter. Its presence would rewrite the first page of any mission script. A lander that was designed to touch a handful of loose rock would suddenly have a solid surface to aim for. The design would need a more robust landing skirt, perhaps a wider base to deal with the planet's modest but non-negligible gravity. I find it hard to picture a capsule that once relied on a gentle, soft touch, now having to brace for a half-Earth-like pull. The first test would likely be a shallow descent, using a test bed on Earth that mimics the new planet's pressure and slope. Rovers would see a shift from roam the hills of a loose aggregate to traverse a terrain that may still be littered with remnants of the original belt. The terrain could be a patchwork of hardened conglomerate and loose debris. Designers would have to balance wheel traction for the firm sections against the risk of sinking into the softer patches. A dual-mode suspension, rigid for the hard parts, flexible for the loose, might become a compromise that fits both. In situ resource utilization moves from collect a few metal-rich nuggets for a test to mine a whole planet for water ice, metal oxides, and perhaps even primitive fuel. The new planet would likely retain the composition of the original belt: metal-rich core, silicate mantle, pockets of ice in the colder regions. A propellant generation plant could be placed at the poles where ice is most abundant, using solar-driven electrolysis. Yet we do not really know how deep the ice lies beneath the hardened crust, and that uncertainty would drive an early reconnaissance phase. Trajectory planning would have to accommodate a new gravitational well. The classic H-type transfer from Earth to Mars skirts the empty gap where the belt lies. Now that gap is a massive body that pulls on the trajectory. The launch window would shift, perhaps narrowing the window for a direct Earth to Mars launch, because the new planet's gravity would need to be either avoided or harnessed. Some mission planners might even design a slings-back maneuver, letting the spacecraft swing by the planet to gain a slight boost toward the outer planets. That approach would demand tighter navigation, and the fuel budget would have to leave room for a mid-flight correction. Navigation itself becomes more complicated. The planet's gravity will create a gradient that subtly alters the path of a spacecraft even when it is not directly aiming at the body. A deep space probe that once passed through a relatively empty region would now feel a gentle tug, enough to shift its arrival time by days. Navigation teams would have to model the planet's mass distribution more precisely, perhaps using a detailed gravity map derived from early orbital reconnaissance. I admit it doesn't quite make sense when you say it aloud, how a gentle pull can become a decisive factor for a mission that is already tight on fuel. The presence of a planetary body offers a new stepping stone for missions aimed farther out. A fuel depot built on the new planet could be refilled from locally mined propellant, then used to launch a probe toward the Jovian system. The fuel pump concept would be less a luxury and more a necessity if the distance to Jupiter becomes more forgiving in terms of travel time. However, the added infrastructure would increase the initial launch mass from Earth, and the design of the launch vehicle would have to accommodate a larger payload. That trade-off would be a central part of any mission's cost analysis. Cost implications ripple through the entire design chain. The first test mission, perhaps a small lander, might be more expensive than a typical asteroid flyby because it would need a more substantial propulsion stage to reach the planet's deeper potential well. On the other hand, a single larger lander could replace multiple smaller missions that would have been needed to sample different asteroids. The overall budget might flatten, but the initial outlay would be higher. It is easy to see the arithmetic, but the exact break-even point would depend on how quickly the planet's resource extraction becomes operational. Design for human missions would also feel the shift. A crude lander that was once thought to land on a loose collection of rocks would now have to handle a more rigid surface, perhaps with dust that behaves differently under low gravity. The dust might cling more tightly to suit material, increasing the risk of contamination inside the habitat. The design of airlock systems would need to account for a tighter seal, and the suits might require a different abrasive-resistant coating. I find it hard to picture the first step of a human hand on a surface that is both familiar and alien. Life support systems could benefit from the planet's potential for water extraction, but they would also have to deal with a more pronounced atmospheric pressure, however thin it might be. If the planet retained a tenuous exosphere, it could affect the performance of solar panels, perhaps scattering more sunlight and reducing efficiency. The design of the solar arrays would need to be adjusted, maybe by adding a reflective coating that compensates for the scattering. The impact on the overall power budget would be a detail that engineers would have to thread through the entire mission architecture. The new planet also changes how we think about the cold start of a mission. Rather than launching a probe that has to navigate a relatively empty void, the spacecraft would now have an intermediate body to perform a first pause. That pause could be used to test new technology, perhaps a new type of propulsion or a deeper test of autonomous navigation, before the spacecraft continues onward. The period spent in orbit around the planet would be a period of test and repair, which could reduce the risk of a failure later in the mission. Yet the added time in orbit would also increase exposure to radiation from the inner solar system, a factor that would need to be fact-checked against the benefits. One practical detail that often gets lost in the big picture is the temperature of the surface at night. The planet's night side would cool more quickly than a planet with a thicker atmosphere, perhaps dropping to well below the dew point of any released water. That could lead to frost forming on the landing site, which in turn might affect the traction of a rover's wheels. A simple observation, frost on a metal footplate, might become the first clue that the planet's thermal cycle is more extreme than expected. The first test of a new navigation system might be a small probe that drops a radio beacon onto the planet's surface, then watches how the planet's gravity nudges the signal. The pattern of the drift could reveal subtle variations in the planet's interior, much like how we infer Earth's inner layers from seismic waves. That kind of gravity sensing would be a new line of evidence that could be collected early, before a full-scale mission is launched. A final detail that catches my eye is the pattern of the planet's sunrise. With the sun rising over a horizon of hardened stone rather than a loose field of rocks, the first light would be reflected off a surface that may be more metallic in tone. The early morning glow might have a faint metallic sheen, a subtle hint that the planet is, at its heart, a collection of the same material that once fell through the void as isolated rocks. The idea of a new planet forming where the asteroid belt now drifts forces us to stare at the equations we trust and wonder whether they are merely convenient shortcuts. In the textbooks, the belt is a leftover, a dead end for material that never gathered enough gravity to become a world. If that material suddenly crossed the invisible line that separates dust from planet, the line itself would have to be redrawn. Scientists would begin by checking the mass distribution thresholds that sit at the heart of every accretion model. Those thresholds are not hard numbers. They are ranges we have calibrated with the few bodies we can actually weigh. A sudden jump from a few percent of an Earth mass to something comparable to Mars would push the upper bound beyond the comfort zone of current simulations. I find it hard to picture how a modest swarm of rocks could rearrange itself into a sphere without a dramatic trigger. Perhaps a passing star or a resonance with Jupiter could provide the nudge, but the mathematics of that trigger is still fuzzy. The giant planets already dominate the architecture of the inner system. Jupiter's gravity carves gaps, shepherds comets, and keeps the belt from coalescing under normal circumstances. If the belt were to overcome that shepherding, we would have to admit that our picture of Jupiter's influence is incomplete. The role of Saturn, too, would need a fresh look. Their combined pull might have been misestimated, or perhaps the belt's composition, more metallic, less icy, gave it a hidden heft. Either way, the notion that a giant planet can be both a barrier and a catalyst at the same time feels uneasy when spoken aloud. Extreme accretion events are rarely featured in the standard suite of simulations. Most models assume a gentle, steady buildup, a slow dance of collisions that gradually smooths out irregularities. To accommodate a rapid, planet-forming burst, we would have to inject high-energy impacts into the code, letting fragments smash together in a cascade that builds a core in a few million years instead of tens. The computational cost of such runs is steep, and the outcomes are noisy. We don't really know whether the resulting planet would be a solid rock, a rubble pile, or something in between. Educational curricula would feel the tremor too. Planet formation chapters in undergraduate courses are built on a tidy narrative: dust, planetesimals, embryos, planets. A real-world counterexample would force professors to add a what-if module, showing students that the boundary between theory and observation is thinner than textbooks suggest. Lab exercises might shift from calculating Hill spheres to testing how small changes in mass distribution affect stability. Students would learn to question the assumptions that have seemed immutable. Observational campaigns would scramble to catch any hint of a belt in transition. Telescopes that once scanned the belt for mining prospects would now be tasked with measuring subtle shifts in orbital inclinations, looking for a collective wobble that hints at a growing mass. Infrared surveys could search for excess heat that a forming planet would radiate. The data pipeline would need new filters, new alerts, and perhaps a dedicated monitoring program lasting decades. It would feel like watching a slow-moving storm, waiting for the first flash of lightning. Beyond our own system, the episode would ripple into exoplanet theory. Astronomers already wrestle with systems that host tightly packed super-Earths and distant gas giants. If a belt can become a planet under the right conditions, then the gap we see between debris disks and full-blown planets might be more porous than we thought. Theoretical frameworks would expand to include a class of belt-derived worlds, and statistical surveys would be re-examined for signatures we previously ignored. All of these adjustments share a common thread: the need to accept that the thresholds we have set are not universal constants but context-dependent guidelines. The belt-to-planet scenario would remind us that planetary formation is not a single script, but a collection of scripts that can rewrite themselves under unusual pressure. It would also make us aware that the instruments we trust, our telescopes, our computers, our textbooks, are all calibrated against a limited set of outcomes. Even as we sketch new equations, the physical feeling of the belt remains unchanged in our minds. A cold, thin ring of rock, the soundless grind of countless collisions. If that ring were to thicken, to feel more like a solid surface under a probe, the tactile image would clash with the silent, empty space we have grown accustomed to. I don't have a clean picture of how the transition would feel, but the thought of a probe's footpad pressing against a newly formed basalt plane is oddly vivid. The scientific community would likely respond with a mix of excitement and caution. Papers would appear, each proposing a different mechanism, each testing the limits of existing models. Peer review would become a forum for debating whether we should broaden the definition of planetary embryo or keep it narrow. Funding agencies might allocate resources to long-term monitoring, hoping to catch the moment a belt tips over the edge. In the end, the scenario would act as a pressure test for our confidence. It would show that the line we draw between dust and world is not carved in stone but in sand that can shift with a gust. The most concrete outcome might be a new set of charts, plotted with finer resolution, marking where mass accumulation becomes self-sustaining. A small, perhaps overlooked detail would be the change in the belt's albedo as it thickens. Its reflectivity would drop, making the region slightly dimmer in the night sky, a faint dimming that could be measured by a careful photometer. When we let a mind wander beyond the data, the ordinary becomes a laboratory for the impossible. That quiet habit of asking, "What if?" has, more often than not, nudged the hard-won facts into new shape. I keep a notebook of those moments, the ones that feel more like a half-remembered dream than a calculation. The notebook's pages are thin, the ink smudged, yet each line marks a point where imagination brushed against measurement. It does not replace the telescope, but it steadies the hand that points it. The notion of a belt of rocks gathering into a sphere feels like a thought experiment pulled from a child's sketchbook. Still, that sketchbook has been the source of many genuine breakthroughs. I find it hard to picture a planet forming where collisions normally grind everything down, but the very difficulty of the picture reminds us how delicate planetary birth truly is. Our models tell us that a planet needs a certain mass to hold onto an atmosphere, yet the asteroid belt never reached that threshold. That gap, a missing planet, is a reminder that the solar system's architecture is not a given. It is a record of countless near misses, of bodies that were torn apart before they could grow. The fragility of that process feels almost personal, as if the system were a fragile sculpture that could shatter with a single misstep. Young people who stare at the night sky often start with a question about that missing world. Their curiosity is not a fleeting spark. It is a slow-burning ember that can outlast a career. When they hear a story about a belt that might have become a planet, they begin to imagine building instruments, launching probes, perhaps even nudging debris with a gentle push. That imagination fuels the next generation of engineers, even if the actual engineering will be far more mundane than the fantasy. There is a quiet unease that comes with the idea of deliberately reshaping a celestial body. We have already altered the moon's surface with landers, and the idea of moving an entire asteroid belt feels like a step too far. Ethical questions rise. Who decides that a region of space may be rearranged for our benefit? What rights, if any, do inert rocks have? The conversation does not settle quickly. It lingers in committees, in coffee-stained drafts, in the pause between a scientist's sigh and the next calculation. The line between hard data and speculative narrative is thinner than a microscope slide. In the lab, we write equations. In the story, we stretch them. Both practices keep each other honest. When a speculative scenario fails, the failure points back to an assumption in the data. When a data set refuses to fit a model, the gap invites a new story. The dialogue is a back and forth that feels more like a quiet negotiation than a loud debate. Even as we plot orbits and calculate masses, a faint feeling remains that we are observers in a place that does not belong to us. The solar system moves on, indifferent to our classifications. Yet our small, persistent curiosity stitches us into that motion, however tenuously. It is a reminder that we are not the center, but we are nonetheless participants in the ongoing rearrangement of matter and thought. I sometimes stare at the cold metal of a telescope's primary mirror, feeling the faint vibration of its motor as it seeks a distant point. In that moment, the mirror seems less like a tool and more like a thin, reflective pond that catches the faint glint of a distant, imagined world.